welcome. We were talking about chemical potential and let us continue discussion on chemical potential. The reason why we want to talk about chemical potential is because we want to talk about the kinetics. Till now we have been discussing about thermodynamics. We said that you can look at some regular solution kind of model and that will give you a free energy. Then you can look at the free energy that will tell you, for example, the system will become immiscible at this temperature or not, or it will be completely miscible, or it will become ordered and so on and so forth. So, the equilibrium structure that your system would get is given by thermodynamics. But we are also interested in knowing the kinetics. How long is it going to take for the system to reach this equilibrium? And obviously, in all the cases that we are going to discuss, which is mostly solid-solid phase transformations, then it depends on diffusion, because diffusion is the one that controls the rate as far as the kinetics is concerned. Okay. Suppose you take a homogeneous system, it wants to phase separate, then all the A atoms have to move to one side, all the B atoms have to move to another side, and how long will it take for these A atoms and B atoms to move is determined by their diffusivities, and that will what finally determine how long will it take for the system to get phase separated. Or suppose if it wants to undergo ordering and it is a homogeneous alloy, then it has to undergo ordering by moving around atoms and adjust them in such a way that you will have an ordered structure. It is short range diffusion, but it is still diffusion that has to take place before this can be. Or if you might have some grains and then grain growth has to take place, then across the grain boundary atoms have to jump and become part of one grain, in the process of which the other grain will disappear and you will have grain growth. So, all these atomic processes are mostly related to diffusion or diffusion itself. So, we are interested in understanding diffusion. Like I said, one of the definitions of chemical potential is to say that chemical potential is the quantity which decides which way atoms will move, and till chemical potential gets equalized, there will be movement of atoms. Okay. Now, let us understand it in a little bit more of detail. So, I am going to consider now two free energy versus composition curves. Okay. So, the first free energy versus composition curve looks like this. Okay. It is a nice parabola kind of free energy versus composition diagram. Okay. Now, I have another free energy versus composition diagram that has this double well potential. Okay. So, now I am going to have two alloys chosen. Okay. Let me call them as 1 and 2. Okay. Now, if I want to know what is the chemical potential for A and B here, all I need to do is to draw a common tangent. So, that will give me mu B, because this is cutting the B, pure B. So, it is mu B, and because this is cutting A, this is mu A for 2. Similarly, I can draw common tangent, and this will again be mu B, but for 1, and this will be again mu A, but this is for 1. So, you can see that the chemical potential for A is higher in 1 than for chemical potential for 2, right. The chemical potential A is higher in 1 than in 2. Similarly, the chemical potential in for B in 2 is higher than in 1, which means what? So, this chemical potential till it becomes equal. So, then when they become equal, what will happen? So, you will have the same tangent for the system. So, this system, suppose if I take 1 and 2, this is alloy composition corresponding to 2, this is alloy composition corresponding to 1, and I am going to weld it together. I am going to keep it at a high enough temperature where diffusion can take place. Then you can see that because the chemical potential for B is higher in 2 than for chemical potential in 1, then the B atoms are going to go from 2 to 1. Similarly, because the chemical potential for A in 1 is higher than in 2, so from 1 the A atoms are going to go to 2. So, what will happen if the A atoms leave from here towards here and B atoms come here, so overall composition is going to come somewhere here. Okay. So, after a long time, so you will see this system will evolve to one in which you will have a homogeneous composition, and that composition will be somewhere here, right. So, this is composition of 2, this is composition of 1. So, it will come to some x naught which is in between. This is what is going to happen. On the other hand, let me choose one system here, let me call this as 2 now, and let me choose another system here, let me call this as 1 now, right. Now, if I draw a common tangent, right. So, this is mu A 1 and this is mu B 1, and for this system then I am going to have it here. So, it is going to go outside of this, but it is going to cut somewhere here. So, this is mu A 2 and this is mu B 2. Now, suppose I take a similar structure. So, I take this and then I take 2, I take 1. Then what happens? You can see that mu B 1 is higher than mu B 2. So, the B atoms are going to start from 1 and they are going to come to 2. Similarly, the chemical potential for A atoms in 2 is higher than for A atoms in 1. So, the A atoms are going to move this way, right. So, in the process what is going to happen? More and more A atoms are going to move from 2 to 1. So, the composition is going to shift towards higher A and the 2 composition is going to shift towards B. We know that whenever you have system like this, then a mechanical mixture. So, it is going to have some free energy somewhere here depending on overall alloy composition, but the end compositions are going to be these 2. So, in other words, you are going to have a system which will get an equilibrium composition for say some alpha and equilibrium composition for some beta. So, the 2 is going to go towards x beta, 1 is going to go towards x alpha. So, instead of a homogeneous composition that you achieved here, here you are going to end up with a mechanical mixture. Of course, this is what we discussed. We said that whenever you have some concavity, the system is going to phase separate and it is going to make a mechanical mixture, and that is what the system is doing, and that is consistent because chemical potential equalization is nothing but minimization of free energy. Okay. So, the systems evolve spontaneously in such a way that the free energy will be minimized. So, when the chemical potentials become equal, the free energy minimization is achieved. So, the way atoms will move under the action of chemical potential is consistent with what the thermodynamics tells you, because this concept comes from thermodynamics after all. So, we are seeing that in these two cases the system evolves in the way you would expect. If you have this mechanical mixture, of course, it has higher free energy, because remember I said if you have 2 compositions and if you have mechanical mixture, depending on the overall composition, the free energy will lie on the straight line connecting them. So, in this case it so happens that this mechanical mixture free energy is higher than if it becomes homogenized. So, the system evolves towards homogenized composition. In this case, because the homogenized system has higher energy, then if it becomes a mechanical mixture, then it can reduce its free energy. So, the driving force in this case also is the minimization of free energy, just that the microstructurally then this should become a mixture of some A rich alpha phase and B rich beta phase, because of which in this case you see that the atomic movements are opposite to what you would see in the case of homogenization. In the case of homogenization, what is happening is that regions rich in A give out A atoms to regions poor in A, and regions rich in B give out B atoms to regions poor in B, so that overall the alloy gets to the same composition. In this case, on the other hand, regions which are rich in B are getting more B atoms, so they are getting richer in B, and regions which are richer in A are getting more A atoms, so they are getting richer in A. In other words, regions which are poorer in B become poorer, more poorer, and regions which are poorer in A become more poorer in A. So, the final solution, the equilibrium solution in these two cases, we have the same type of weld 1 and 2, one is A rich, 2 is B rich, and depending on the free energy versus composition curve, you will see that it can either lead to homogenization or lead to phase separation. If it leads to homogenization, then A rich regions actually give out A atoms, B rich regions will give out B atoms, but if it becomes phase separated, then B poor regions will give out B atoms and A poor regions will give A atoms. Okay. So, as you can see, we have discussed these two types of free energies, and we said that this happens when omega is positive and this happens when omega is negative or omega equal to 0. Okay. So, we can see that the case where you have omega equal to 0, for example, will lead to homogenization, whereas if you have a system like this, which will lead to miscibility gap, and this is what you are actually seeing here. So, in terms of the chemical potential, we are seeing that things are consistent. Okay. In terms of chemical potentials, atoms move from regions of higher chemical potential to lower chemical potential. If you take A atoms, you find out what is the mu A in one phase, what is the mu A in other phase, whichever is higher in A will move towards lower in A, till the mu A becomes the same in both the phases. Similarly, if you try to look at what is mu B in phase 1 and mu B in phase 2, it will go towards the case where mu B becomes equal in both the phases. Okay. In the process, the phases themselves disappear, so it becomes a homogenized phase in one case, for example, or it becomes some end composition which is A rich or which is B rich in the other case, for example. So, in terms of our definition of chemical potential, this is the reason why we define chemical potential. So, chemical potential or partial molar free energy basically tells you what happens to the system's free energy when you add a particular type of atom. Okay. Mu A, which is the chemical potential for A, for example, tells what happens if you add A atoms. Using this chemical potential concept and using the construction, namely that if you can look at the free energy versus composition diagram, at any composition, if you draw a common tangent to that curve, then where the tangent cuts the pure A, pure B lines on the y axis, basically gives you the chemical potential for A and B for that particular system. Using this, we can actually understand how diffusion is happening in two different cases. I have welds which are made up of A rich and B rich alloys, and when they are welded and when they are allowed to interchange atoms, that is atomic flux is possible, you keep it in a furnace or at some high temperature where diffusion can take place, then you will see that in one case it evolves in such a way that it produces homogenization, in other case it produces a more and more inhomogeneous structure. Okay. So, this is, but this is consistent with chemical potential, this is consistent with free energy minimization. In both the cases, it is driven by, because this is a spontaneous process, which means it should be minimizing the free energy. So, it is actually minimizing the free energy. In one case, you found that mechanical mixture has higher energy, so it is becoming a homogeneous mixture. In the other case, you found that mechanical mixture has lower energy, so it is becoming the mechanical mixture of the required composition. Okay. So, chemical potential and free energy minimization, they are all the same, and we are finding consistent behavior in this system. Okay. So, we will now discuss the same process in terms of composition of A or B, and then try to understand it a little bit better. Okay. That takes us to what is known as classical diffusion and Fick's laws. That is what we will do next. Thank you.